Welcome to our 4 p.m. press conference. This is on rain on snow floods in a changing climate. And our speakers in this order are Nick Wayand, PhD candidate in the Department of Civil and Environmental Engineering at the University of Washington, in Seattle, I assume. Okay. Danny Marks, research hydrologist with the USDA Agricultural Research Service in Idaho. Where in Idaho? Boise, Idaho. John Pomeroy, Canada Research Chair in Water Resources and Climate Change and Director of the Center for Hydrology in the Department of Geography and Planning at the University of Saskatchewan. And what town in Canada?
In Saskatoon.
Saskatoon, I've been there.
No, you have to say that, Saskatoon, Saskatchewan.
Okay, Saskatoon, Saskatchewan.
Very good.
All right, and last is Stacy Demonsky. She's a master's candidate at the Center for Hydrology, at the same place in Saskatoon, Saskatchewan. Thank you.
You're up. All
right. Good afternoon. Today I'll be starting out by looking over the domain of the West Coast U.S. mountain range and focusing on answering the question of how important is snow during rain-on slow floods. This work was really motivated to answer the question, how important is snowmelt during these largest rain-on snow events to water managers and flood forecasters. So the results of our modeled study was that it could range up to 23% of the total contribution to flooding. And this snowmelt, amount of snowmelt really depended on the basin area shape and the forest cover and the elevation of the rain-snow transition throughout the storm. So just to start out, show a time-lapse video in Snoqualmie Pass, Washington, for this last winter year. And this is located in the rain-snow transition where we have these rain-on-snow events. Right about now in March, we have a medium rain-on-snow event. And at these point locations, we can quantify how much snowmelt and how much rainfall are occurring. However, these great research stations aren't available everywhere in the basin. So it's more difficult to quantify the total amount of snowmelt happening over our entire basin. So a rain-on-snow event really occurs with the previous storms that happened in that year. So during a typical storm, we have the elevation that's separating the snowfall from rainfall. So below this elevation, you can think of the rainfall is contributing to runoff and flooding, while above it, the snowfall that's being held for future use in spring and summer. However, during our later rain-on-snow event, we have a higher transition from snowfall to rainfall. So we have a larger area that's contributing to runoff, and this is driving a large amount of why rain-on-snow events have contribute to more flooding. In addition, we have this area of snow cover that can be exposed to warm, windy, and humid conditions, which has the potential to drive large snowmelt. And this depends mainly on how much snow you had there to begin with, the area of that basin, if there's a large amount of area or a small amount, and also on the forest cover, which reduces the wind speed that's really driving the melt during these events. So how do we maximize snowmelt? You can think of a typical distribution of snow depth with elevation, where we have more snow depth at higher elevations, but we have more energy for melt at lower elevation, where it's typically warmer. So we really have this sweet spot in the middle where we can have the most amount of melt. So our study really attempted to include these three factors that control how much snowmelt contributes to rain-on-snow floods by looking at the elevation of the rain-snow transition, if there was a smaller area or a larger area, and then also looking at the shape of the basin, which can be very important. If you have a uniform area, elevation, or maybe you have a lot of area at mid-elevations. In addition, we also looked at the forest cover, which I mentioned reduces wind speed, and wind speed is really driving a lot of the turbulent heat flux that can cause large melt rates. So we focused on 3 basins, one in Snoqualmie Basin in Washington, and then one in the central Sierra Nevada and in the southern Sierra Nevada, and looked at a range of the top 10 storms over a 30-year period, and estimated how much during that storm was contributed from snowmelt. And so our range varied from 0 to 23%, which provides a bound on how much snowmelt matters during these floods. So you can see it varies by storm dramatically, but also between each basin. And finally, I'd like to make a plug for a high school rain on snow lesson that we've developed, which can be found here, that outlines a lot of the basic principles and that might be useful for high school teachers to use in their classes. Thank you.
All right, now let's see if I can make this go. So, oh, you have to start it, don't you? How do you do that? Down right there, okay, gotcha. So I'm going to talk about what's going on with the mountain snow covers in the western U.S. and why rain on snow has become more of a problem perhaps than it used to be. And the reasons for that really have a lot to do with, how do you make it advance? Okay, the reasons for that have a lot to do with what's been changing in the western mountains, and the thing that we all understand pretty well is that temperature's increasing. Temperatures have gone up 2 to 2.5 degrees over the last 50 years. And, but one thing that's really critical to the condition of the snowpack is the humidity. And it's harder, we measure humidity in fewer places, and it turns out that the humidity is increasing during storms, but not really increasing between storms. And that humidity increase during storms is very important to the sensitivity of the snow cover, because in western systems, at least in the United States and even in southern Canada, our systems are pretty close to the triple point of water. And so any change in the humidity has a big impact on the condition of the snowpack. This shows some of what's going on. So what's happened as the temperature's gone up and the humidities during storms have gone up is that the ratio of rain to snow in the mountains has changed. And these are data from the Reynolds Creek Experimental Watershed, where we measure snow very carefully across an elevation range from around 3,500 feet up to about 7,500 feet. And so you can see that in the upper part of the basin, it started out in the 60s as mostly snow with a little bit of rain, and it's still dominated by snow, but there's a lot more rain and less snow than there used to be. Snow's gone down by about 16%. At 5,400 feet, it used to be about 50-50 rain and snow, and now it's rain dominated. And at the lowest elevation measurement site, 4,000 feet, what used to be rain dominated but close to 50-50 is now almost all rain. It very seldom snows there. So there's been a big change over the last 50 years. But what does this mean to the landscape? In Reynolds Creek, if we look at 68 to 2006 and mass weight the events, we can figure out what the rain-snow elevation, transition elevation was for individual storms for each of those years. And what we've seen from the data is that the rain level is going up by about 108 meters a decade, and the snow level is going up by about 108 meters a decade. And if the problem with that is that the elevations have limits, they only go up so high, and so you run out of area and you run out of snow as this continues on. This is a graph of that, and starting in the mid-60s. And the gray area is the transition zone, where it would be a mix of rain and snow. And you can see that in the mid-60s, most of the watershed, the line at the top is the highest elevation in the watershed. The line at the bottom is the outflow. at the beginning of the record, it was mostly snow with a little bit of rain at lower elevations and a transition zone. As we move on into time, now only about 5% of the precipitation is the area of the watershed is totally snow dominated. A fair amount of it is in the transition zone, but a lot of the watershed is now rain dominated. We can put this out in a map and see what the watershed looked like in 1968. The yellow area is the rain-dominated area, the blue is the snow-dominated, and the gray is the transition, and compare that to 2006. Only the uppermost parts of the watershed and the southern end, where the high elevations are now totally snow-dominated. Well, we can take that and move it to California by imposing the same trend and look at what was going on in 1968. And we see there that most of the upper parts of the Sierra Nevada, the interstate would have gone right up through here, I believe, and over Donner Summit. And so most of the Sierra Nevada was snow dominated, but the lower areas of the American River Basin down towards Sacramento were rain dominated. By 2006, it looked more like this, with a mix of rain and snow even down to the lake level. And the snow-dominated region is much smaller towards the higher parts of the mountains. Now, we have to recognize that the Sierra is lower along the Tahoe Basin there than it is in the more southern parts, but the snow-dominated area has been reduced, and if we just take that trend and move it on out to 2044, then we're having rain at the lake, and only the highest of the mountains are snow-dominated. So the changes are going to be significant, and a small change in the humidity can really lead to a large change in what the snow cover turns out to be. In warm snow years, the sensitivity to humidity increases is stronger than during cold years, but in drought years, it's very sensitive to increases in humidity. And those of you that are from California, and note that this last year was one of the smallest snowpacks in history, though it may not have been the lowest in precipitation. I think that the last year, the last really dry season, had a slightly larger snowpack, but had less precipitation than this one the previous year. And that's it.
Well, good afternoon, and thank you for coming. There we are. So we're going to move a little bit further north to the Canadian Rockies, which are the headwaters of the Saskatchewan and the Athabasca River systems in Western Canada, but also the headwaters of the Columbia River system that feeds the Pacific Northwest of the United States. And it's a much colder place. If you think of the national parks such as Banff and Jasper, that's the environment we're talking about. And what we had was an exceptional flood in 2013. It was driven by rain, and there's nothing exceptional about that, but we'd never had a rain-on-snow flood in recent memory. There are some anecdotal evidence of these in the 1800s in the area, but nothing recently. And so when you see a climatic event that's not occurred before, those things without statistics become strong indicators of a changing climate. And in fact, this one woke everyone up because it was the most expensive natural disaster in Canadian history, with $6 billion of damage and 100,000 people evacuated from the city of Calgary, Alberta, which has 1.2 million people. So what happened? After a fairly cool spring, where we still had mountain snowpack sustained at high elevation, we had 250 millimeters of precip occur over 3 days in late June and right around June 20th. We had large snowdrifts up near the tree lines in the area because of the cool spring, and so the rain fell on the snow. That, in many areas, such as has been discussed in the United States, will promote large floods in midwinter. But here's one in midsummer that's occurring from the same process. And what we found is it was a little bit different. We didn't see an acceleration of the snowmelt rate. It actually decelerated because we're near the summer solstice, and the cloudiness associated with the rain on snow reduced the solar radiation energy driving snowmelt. And the reduction was so large it couldn't be replaced by the extra energy coming out of the warm rain and the atmospheric energy being transferred by turbulence down to the snowpack. So so it was a little bit different, and that's probably a very good thing. If we had had the high energy associated with some midwinter US rain on snow events, it would have been much, much worse in Calgary. And as it was, there was loss of life, but it was 4 or 5 people. It wasn't massive loss of life. Snowmelt was 1/3 of the inputs to the flood out of the Alpine in this period. So that compares quite favorably with the highest numbers you're seeing out of the Pacific Northwest. And when we looked at the timing, the runoff of the snowmelt was split between flow overland and that traveling through the soil, and which meant that there's a lot of groundwater recharge, which came out much later afterwards. A key message from this is that, yes, it was the largest disaster in Canadian history, but that flood would have been much worse if warmer rain had occurred and if the conditions had been warmer during this. So it's kind of a new, cool rain on snow event that we haven't quite seen before. To give you a picture of it, this is the landscape we're talking about, the Alpine zone in the Canadian Rockies. We get very, very deep snow, and it persists up there well until June quite often. So we're raining onto that landscape, and at lower elevations there isn't any snow. When we looked at the water balance before and after the event, the week before, the week after, and the week of the rainfall event, you see there was very little coming in the weeks before and after. It wasn't flooding. The substantial rainfall, that's the green bar coming in, and then snowmelt added up on top of that coming through there. And then coming out, split 50-50 overland and subsurface runoff. Still quite a bit of flow coming out the week after, sustaining stream flow for some time afterwards. You could actually see the mountains. They looked like they were weeping wet rock faces for quite a long time. And this illustrates the energy flows into the snowmelt before the flood and after the flood. There was more energy going into snowmelt than during the flood. So the rain on snow itself didn't actually increase it dramatically as it would elsewhere. It actually decreased it, and that was good. This is just showing the types of amounts of precipitation we had. It was around 250 millimeters at all elevations during the flood, and that was a very interesting thing. Normally we get more rainfall as we go up in elevation in the mountains. In this case it didn't happen, and that rain started off very warm. It's still being investigated, but some atmospheric scientists think that there were aspects of a tropical rain event in this storm, which again would be utterly unique at the northern latitudes where it occurred. And you can see the rainfall amounts were very heavy in the mountains west of Calgary, and not so much out in the prairie in that environment. So just give you a bit of a picture of this event, very, very unique. And we're quite concerned now because the flood defenses in Western Canada and the water management systems were built with snowmelt being driven by warm temperatures and solar radiation, not by rain events, and rain coming much later in the year. And so getting these mixed events is creating situations where we are having to re-engineer our cities, our reservoirs, look at the reservoir rules of operation, and reassess the potential for hydroelectricity generation. And that has implications not only for our part of the world, but even down into California, where much of that electricity is exported. Thank you.
All right, good afternoon. I'm going to move you guys around again, and we're going to go into the Canadian prairies now, and I'm going to talk to you about the impact of increasing rainfall and rain on snow on flood generation in that region. So on the Canadian prairies, we have actually experienced some changes in climate. We have seen warming temperatures occurring, and this is causing a change in the phase of the precipitation. So we're seeing an increase in the rainfall amounts and a decrease in the snowfall amounts in the region. And with that increased rainfall, we're seeing it occurring in certain times of the year. So in March, we're seeing substantial increases occurring, and this is significant because in March, you still have the snow on the ground. So if you increase the rainfall in March, you're increasing that incidence of the rain on snow events that can occur. And then also in May and June, we're seeing the increasing rainfall. And this is occurring when just after that snowmelt period that occurs in April. So the basin is all wet from the snowmelt period. So if you increase the amount of rainfall during that time period, it can have implications for stream flow in that region. And then also in October, there's increasing rainfall. And that can influence actually the snowmelt that occurs the following year. So if your soils freeze when they're wet, then in the springtime, it actually restricts the amount of snowmelt that can infiltrate. So it increases that snowmelt runoff. So given these changes in climate that we've seen drastic changes to the stream flow in the region. So even though we've seen a decline in the snowfall amounts, we're actually seeing an increase in the snowmelt contributions to stream flow by about 5-fold. Rain on snow contributions to stream flow has increased even more by 34-fold increase. So that's quite a substantial increase that we're seeing. And then rainfall has also increased by about 150-fold. And all these changes have occurred since about the mid-1990s. So even though we're seeing these changes in climate and they're driving changes in the stream flow on the prairies, the Canadian prairies, the magnitude of these changes might be amplified by the wetland drainage that has been going on for decades. So future flood predictions are needed to further consider the increasing importance of the rainfall and rain on snow processes due to those changes in climate and wetland drainage, as they've been responsible for absolutely massive flooding that cost billions of dollars on the Canadian prairies, with 2011 being a very widespread rain on snow flood event, and also again in 2014, the eastern portion of the Canadian prairies experienced a massive rainfall event that caused huge flooding, again costing billions of dollars in damage. So the study site that I looked at for my research was the Smith Creek Research Basin, and it's located in southeastern Saskatchewan, Canada. It's very much an agriculturally dominated basin, and it's located in the prairie region. So I mentioned to you that wetland drainage can increase that magnitude of the climate changes, and this is why. If you look at the picture on the left here, you can see that there's no wetland drainage that has occurred in that region. So that surface runoff that is generated drains into the depressions on the landscape, so that landscape holds that water. It doesn't contribute to stream flow. But in the picture on the right, you can see that that water goes through those drainage channels formed, and it contributes to the stream flow. So in the Smith Creek Basin, we've actually seen a substantial loss in wetland area of about 58% between 1958 and 2009. So it's a drastic loss to that wetland area in the region. So given those changes with the climate and land use, specifically wetland drainage, we've seen an increase, like I said, in those various runoff mechanisms. And this has resulted in a 14-fold increase in annual stream flow volumes. So they've increased from about 3,000 decameters cubed per year, now up to over 42,000 decameters cubed per year. So that's massive. So not only are we seeing that increase in stream flow, but we're seeing a change in the contributions to stream flow. So during that first time period of 1975 to 1994, you can see that snowmelt accounts for about 86% of the annual stream flow volume. And that's well within the expected over 80% on the Canadian prairies. But since then, it's consistently declined down to just now 47% of that annual stream flow volume is being composed of snowmelt runoff. And this is being taken up by increases in the rain on snow runoff from 7% all the way up to 19% now of the annual stream flow volumes. And then rainfall runoff has also increased from 7% up to 34%. So combined, we're seeing rainfall and rain on snow runoff processes account for over 53% of the annual stream flow volume, and that's vastly different than the historical about 15% on average. So when looking at the floods in the basin, you can see that there's been 4 flood years that have been recorded, with the first one being in 1995. And this one, as you can see, is very much a snowmelt-dominated flood event. 99% of the stream flow that year was from snowmelt processes. And then switching over to 2011, you can see in the picture down here, you can see that massive rain-on-snow event occurred. In this year, there was a record-breaking snowpack that accumulated over winter, and then a large rainfall event occurred while that snowpack was melting, and it caused widespread flooding across the eastern portion of the Canadian prairies. So as you can see in the picture there, that's the gauging station, and it's well underwater. And underneath that whirlpool there, there's a culvert that's actually underneath there. And then again, in 2012, flooding occurred again. So this flood wasn't as large as you can see in the photo. It wasn't the largest flood on record. But what was very interesting about this flood was that it was the first ever rainfall-driven flood on record. So 76% of that stream flow was derived from rainfall runoff processes. And you can see the nice greenery in the background of the picture. It's during the growing season. So this is just, it was just completely different for this basin. And then again in 2014, we had another massive rainfall-driven flood event. And the unique part about this one is that it actually broke peak stream flow records. So as you can see in the photo here, it's quite substantial. The flood is actually larger than the 2011 flood for peak, but volume wasn't quite as large. So as you can see with these flood-generating mechanisms, you can see that there's this increasing importance of that rainfall and rain-on-snow processes occurring, causing flooding in the Canadian prairies. Thank you.
Thank you, speakers. Do we have questions?
Rick Lovett, freelance. I think my question is probably for Nick and maybe for Danny. I come from the Pacific Northwest, and where we get atmospheric rivers just like we're having around here today. And I remember a giant flood in Portland where we got one of those that landed on snow. The models are showing an increase in severity and frequency of these things, and I'm wondering if that is going to be a problem or if they're going to come down as snow rather than rain.
Well, I think it's an interesting question. If you are having to have a large snowmelt-driven flood, you have to have a lot of snow to begin with. Thank you. And then a large warm atmosphere river to come in behind it. So I think the variability of these going from a large cold period to a large warm period is very important. How that will change in the future will be an active area of research.
So if the flood you were referring to is the 96 flood? Okay, so if you remember, in 96, the month of January had been extremely cold. There was snow almost down to the Willamette Valley floor prior to the rain event. And so that was a major rain-on-snow flood. And then a year later, had a similar warm storm come in, but it was warm prior to that storm, and so there was really no snow. And so a lot of the damage from that the next year was from mudslides, similar to what's happened in Southern California here this last week.
Other questions? And just to mention, questions are only from members of the press. Any questions from the chat? Okay, that wraps it up. Thank you very much. Thanks everyone for coming. We have our next press conference is tomorrow morning at 9 a.m. It's on first results from NASA's Orbiting Carbon Observatory. And if any of you do social media about science, I encourage you to come to an event at 5 o'clock. We're going to have a social media forum in this room where people are we'll have a panel and then a discussion afterwards about using social media to communicate about science.